Welcome back to the New Quantum Era. I'm your host, Sebastian Hassinger. This is the podcast where we interview people working in the field of quantum technologies, quantum computing, quantum sensing, quantum networking, which are very much in the earliest stages of their development. And that's really one of the things that I find the most fascinating and compelling about the topic is the early stage that it's in. I like to say that, it's not like we've reset the clock to the beginning of the internet era in the 90s or the beginning of the PC era in the 80s, but really we've reset the clock to something like the late 40s or 50s when there was still a lot of uncertainty about how to build computers and how to even build the basic unit of computation, the transistor, or before that, obviously, the vacuum tube. And we have defined a qubit at this point in quantum computing as a two-level system that's controllable and measurable, and we can perform logical operations on it, but not necessarily come to a consensus on how to build a qubit. The ones that dominate the news these days obviously are superconducting or atom-based qubits, neutral atoms, or ions from various companies. But there are other modalities that have been tried, like NMR, that are still in the process of being developed, like photonics and spin qubits. And spin qubits is what we're going to talk about today. These are systems that are built using the traditional fabrication methods from microprocessors, from classical silicon. And they hold the promise for the future of quantum computing in many ways because of the advantages of leveraging those CMOS and other technologies. So today, the last interview that I conducted at APS was with Andrew Dzurak, who is the founder and CEO of Diraq, a quantum computer company based in Australia that is experimenting with quantum dots. And I learned a ton from Andrew. It was a really interesting conversation. So I hope you find it interesting and educational as well. Here we go. Thank you very much for joining me, Andrew. I'm really looking forward to the conversation.
Me too, Sebastian. Very much looking forward to it.
So let's start with what's special about Diraq. I mean, you are building qubits, and they're a different type of modality of qubits than I think people are probably more familiar with who've been tracking the industry, right? Superconducting, trapped ions, neutral atoms more recently. There's been rumors of photonic qubits for years, but you're building spin qubits or silicon spin qubits, right?
That's right. Our technology, the basic concepts go back, over 20 years. But the first demonstrations of spin qubits are really only about 10 to 15 years ago. And the particular flavor of what we do, which is we modify standard silicon transistors, and inside the transistor structure, we confine or trap single electrons in those transistor devices, and then we use a property of the electron known as its spin. It's like a tiny magnetic moment. Think of it as a compass needle pointing north or south, and we encode the quantum information, the ones and zeros, on the direction of that spin. And so this technology, we've been working on it for nearly 20 years. So it's kind of like a overnight success, 20 years in the making sort of thing.
Yeah. Exactly. Quantum dots go back to even like early 80s, I think, originally, right?
That's right. The very first studies of behavior in at the time they were tended to be called semiconductor nanostructures. Now these days, all transistors are nanostructures, right?
Right.
Effectively, the term quantum dot is actually a broader term than the type of we use a particular type of quantum dot device.
Right.
The general term quantum dot means any structure that is small enough that the behavior of the electrons inside that structure show quantum-like properties due to the confinement. When you make something very small, quantum properties become more apparent. At a macroscopic level, they're very hard to see. And so people are probably much more familiar with things like quantum dot technology used in, let's say, display screens and so on, right? That's a different type. So that's where you have a tiny nanocrystal where, again, the electrons have these quantum properties, but in that case, you're using the specific energy levels of those states to emit light at particular frequencies or wavelength. That is an optically active quantum dot. But we don't use that type of structure. In our case, the quantum dot is just formed by the very small size of the electrode, much like the electrode in a transistor. And because that's only a couple of tens of nanometers across, when you have an electron sitting underneath that, you get these very strong quantum properties. The energy levels are quantized, and importantly, the spin is quantized and accessible.
Right. So essentially, as you said before, it's a single electron transistor, essentially.
Yeah, it kind of is. Got to be a little careful with that terminology, though, because there is actually a specific device called a single electron transistor, which annoyingly does not have single electron in it. It actually can have many electrons, but the operational property of that device relies on the quantum tunneling of single electrons through the device.
Got it.
And to be even more confusing, we use single electron transistors not as the quantum bits, but as the readout sensors that are observing our quantum dot qubits. So there you go.
And the single electron transistors, I think they're also used in scanning electron microscopes. Is that right?
They can be, yes. There are certain types of scanning probe microscopes that do use single electron transistors. And the reason for it, much like the reason we use them, is it turns out that they are the world's most sensitive electrometers. An electrometer is a device that can measure a very small change in local electric potential. And a single electron transistor is the most sensitive electrometer. In fact, it can measure changes as small as a millionth of one electron charge in a device. And we use that sensor, in fact, in the readout of our single electron quantum bits.
So you have a practical application of quantum sensing inside your quantum computer.
We do billions. Really cool. We do billions of quantum sensing experiments every day on our devices. Yes.
Amazing. So obviously, there's two things that sort of jump out from your introductory explanation. One is that you're operating at very, very small scale. So these qubits are very small devices, each one individually.
Yep.
Whereas something like a superconducting qubit is using electrons en masse in a relatively large device to be a quasi-particle. You're actually acting on the electron spin directly.
Correct.
And the other thing is you're in a position to leverage silicon and leverage CMOS technologies to fabricate these devices, right?
Correct. In fact, that really is the key reason. I mean, that's the underlying concept of our company, Diraq.
Right.
It is to use standard manufacturing, both because it is convenient to do manufacturing and it's proven to produce high-yield electronic devices. You can make many millions of those devices reliably. But the other aspect is that they are already very small. So you mentioned size comparison.
Right.
So we are able to fit millions of these silicon quantum bit devices on a single silicon chip, similar size to the silicon chip in your phone or laptop. Whereas if we take, for example, a superconducting qubit, it tends to be at best tens and typically hundreds of microns across, whereas we are tens of nanometers. And so when you convert that length scale to a surface area, that's a factor of millions.
Right.
And so,
so that's clearly, and as you said, if you can tap into 60, 70 years of CMOS technology for fabrication and design, for that matter, then you clearly can. That'll give you a head start in scale and reliability and manufacturability and all of the things that a technology requires to really hit that inflection point and really take off for mass deployment, mass adoption. So you're sort of looking ahead to these devices proving some kind of quantum advantage that the market wants, and you'll be able to supply that demand when that time comes.
That's right. I mean, so the bottom line, and the reason that we've taken this approach is because while there's some fantastic efforts out there in trying to find nearer term uses of smaller scale quantum processing units with maybe thousands of qubits, it is generally accepted in the community that are seriously looking at quantum algorithms, real use cases, that you're going to need systems with thousands of logical qubits, at a minimum hundreds of logical qubits, and that pretty much means you're looking at millions of physical qubits.
Right.
And then if you need millions of physical qubits, you have to work out how to make them reliably, and you also want to make them small enough that your overall system is economical to build.
Right.
And so we've designed now a system that will go to many millions of qubits that can sit inside one single refrigeration unit, pretty much the size of a rack in a data center. So for just a couple of square meters, we're able to build something that it will be an error-corrected, fault-tolerant quantum computer with, tens of millions of qubits. So that's really the heart of it. And, the big step for us, because you were talking about the CMOS manufacturing, we had just over 10 years ago did the first demonstration of one of these quantum bits based on a MOSFET transistor. Showed it worked, showed we could do 1 qubit and 2 qubit logic, but it was all made in a university clean room facility, which is very much, it's like a very, experimental. And so while, we made devices there for a decade, and it produced, a whole string of papers in Nature journals where we showed all of the basic operations and concepts. That is not a scalable pathway. And so the big step for us over the past 2 years, we only founded the company 3 years ago, and immediately formed very close relationships with foundries, both in so GlobalFoundries in the US and IMEC in Europe. And literally just in the last 6 months have now shown that on full-scale 300 millimeter wafer manufacture, which is the standard manufacture in chip foundries, we can make qubits just as well, and in fact better than we were able to make in our experimental environment. And these qubits show very high fidelities, all fidelity metrics above 99%, which is a crucial metric for quantum computing.
That's amazing. You mentioned error correction and fault tolerance. Is there the layout of the qubits? Is this something that you're going to be able to sort of do a native implementation of surface code, or are you going to have to come up with your own approach or some sort of modified hybrid approach?
Yep, it's a very good question. So the nice thing about the surface code is that it works on a two-dimensional grid, a two-dimensional layout. One of the things that's the strength of our qubits is also one of the challenges, because they are so small. Getting in a dense two-dimensional grid is challenging, and so what we've designed are, let's say, smaller modules. Still, we can still fit many, many millions on a chip, but these are not necessarily fully. They're not like 1,000 by 1,000. I can't go into the exact layout because that's proprietary. You can understand, but to give you a general idea, it's not like a full dense two-dimensional grid, but there are, let's say, regions of qubits, and we actually move electrons around along these pathways.
On your website a few days ago. That how I mean, when you think of silicon transistors, those are fixed elements on the chip. How are you moving qubits around on the chip surface?
So just to step back and explain how a MOSFET transistor works in a traditional microprocessor. On the top is a piece of metal, so it's called the gate electrode. Underneath it, you have an insulator, which is typically silicon dioxide or another good insulator. And then underneath that is the silicon. and it's in the silicon where the electrons sit in the transistor. You put a positive voltage on that metal electrode, and underneath the insulator it draws electrons in the silicon, and those electrons carry a current which is what the transistor, it's the current is either turned on or off in the transistor, a 1 or a 0. In our case, we have our electrons sitting underneath that gate, just like in a transistor, but we just have one electron, or sometimes we group in odd numbers like 3. And so in order to move the qubit, we actually just shuttle the electron along the surface of the lower surface, and we have the gates on the surface that kind of, by changing the voltages on those gates, they kind of move
Drag it along.
That's right, exactly. They drag along, and it's often called a bucket brigade type process. And this technique is not a new technique. So the idea of moving electrons around in these sort of silicon CMOS devices is used already in what are called charge-coupled devices. So it's a standard thing in imaging technology and so on. So the only thing that we're doing that's a little bit more advanced is when we're moving, not only are we moving just single electrons, but we're carrying their spin information with them. And we're carrying that quantum encoded information on that spin, which moves around the processor.
That's really fascinating, because it sounds like, one of the, for example, neutral atoms as a platform, one of their strengths is that they can, with those tweezers, they can entangle qubits and then move them around.
That's
and
right.
Get all connectivity. It's a very plastic environment. You can reconfigure your operating environment according to the next step you need to take. That I didn't realize you could actually do that in silicon spin qubits as well. That's fantastic.
Absolutely. And in fact, look, there's many similarities. All the different modalities are trying to solve the same problem, and we're just using slightly different physical ways to do it. So in the case of both ion traps or neutral atoms, they move either the ion or the atom around, the array in order to bring one qubit closer to the other. We're doing exactly the same way, except we move it inside the silicon, and we use electrostatic voltages on the gate electrodes to shuttle those electrons around. So, but now we all we might use slightly different architectures. We might be using slightly different error correction protocols. But at the end of the day, we're all doing the same thing. Okay. And so the differentiation really comes down to, are you able to do it in a conveniently manufacturable way, and can you get a lot of them in one small chip?
Right. So let me take, I've got two questions. One is just staying on that shuttling, and also including gate operations. What's the speed of those operations like? How quickly can you move a qubit from one location to another?
Yeah, well, actually moving the qubits is one of the fastest things we can do. So we can move an electron over a significant number of qubit locations in nanoseconds timescales. Yeah, so a few nanoseconds. The gate time operation is typically somewhere between 100 nanoseconds and 1 microsecond. So, we quickly move them around much faster than we need to on the time of doing individual operations. One other thing that's important to note, and one of the reasons why we believe that the silicon integrated approach is so attractive, is that everything is essentially done just by pulsing on and off voltages on these electrodes. So it's extremely analogous to the way that modern microprocessors work. And actually, I do want to come back to something you mentioned right near the start of our discussion, which was not only are we able to leverage the manufacturing technologies from CMOS, but we can also leverage the design technologies. So we've just in the last year designed a chip that's been made for us by GlobalFoundries, and we designed that chip, which has classical transistors monolithically integrated on the same chip with quantum dot qubit devices. And the whole chip was designed using a standard electronic design application software, Cadence. Cadence and Synopsys are the two main chip design. And we happen to use Cadence for this one, and that's an enormous advantage, because having all of the tools that are already there, not having to reinvent the wheel, is incredibly valuable.
Well, and not only that, the skills to use that application are out in the marketplace. So you're not starting from somebody who's maybe a PhD in quantum physics but hasn't actually designed silicon before, or used the Cadence tool. So that's great. And then also the applications are aligned with the operation of the whole tool chain. So you're sort of dropping in with a design that I would assume is largely already compatible with the way the fab is operating that
That's
line
right.
anyway.
That's
Yeah,
right. And
incredible.
and actually, it's interesting significant you mentioned training and experience of the team, because one of the things that our team has an amazing array of quantum engineers and scientists who are familiar with operating quantum devices. But when we had to design these chips, we ended up hiring people from the conventional CMOS chip design
Right,
industry to help
right,
do that design, who didn't even know what a qubit was.
right.
And so they're working alongside our qubit team and in a tight integration loop. So yeah, I mean, the fact is then we're able to leverage not just the toolkit, but also the experience of people who are very, very experienced chip design engineers. Because many of the ultimate problems of scaling something up to the million qubit level, a lot of it is classical microelectronics.
Yeah,
Because a big part of a quantum computer is the classical control and readout
right,
circuitry that is
right.
required. In
Yeah,
fact, it's an equally hard problem to developing the qubit components is
yeah.
developing all of the classical circuitry to control that well. And when you can do that in a tightly integrated way with CMOS, it's a
Right.
huge advantage.
I was going to say you were mentioning, all of the classical components and elements within the chip architecture. So that's all sitting in the fridge.
Correct,
You're
correct.
not using superconducting, so I assume the fridge is there for essentially for reducing environmental noise and isolating the qubits from the environment, right?
That's right. Technically, the reason for the low temperature is that um, when you've got single electrons in a very uh, sort of tightly controlled state, what you don't want is thermal noise that kicks them around
Right.
and jostles them somewhere they don't want to
Yeah.
be. That's why we got to cool down. But we superconducting qubits operate at the millikelvin
Right.
regime, a few thousandths of a degree above absolute zero. We operate at the Kelvin regime, so 1 Kelvin, which you know to kind of human beings who are used to living at 300 Kelvin,
Yes.
the difference of 1 degree Kelvin doesn't seem very significant. But if you're an electron, the difference between 20 millikelvin, where superconducting qubits are, and 1 Kelvin is a factor of 20. And if you
Right.
translate that to human terms, the surface of the Earth is 300 Kelvin. If you go 20 times hotter than 300 Kelvin, and you're up at 6,000 Kelvin, then you're kind of on the surface of the sun.
Right.
So, so actually, this is a huge difference at the level
Right.
of quantum operation. And so, what it means is also at that temperature, we can run conventional CMOS
I was going to
electronics.
say. Right.
And we've actually recently done this with a team that had been working at Microsoft Quantum in Sydney.
Right.
They've recently, the team demerged from Microsoft. They basically become their own independent
Yes.
company. I think they're going to make an announcement about it soon.
Oh, cool.
They did a bit of a soft launch at the APS conference this
Nice.
week. But that team developed a chip that can be used to control qubits, and we've now used that to control our Diraq qubits, all in one module, sitting at the same temperature
In the
stage.
fridge.
That's right.
So you won't have the sort of large room temp electronics racks that you see around a superconducting fridge.
That's correct. That's correct.
Yeah.
To be fair, it's important to note that the superconducting community and others are also developing
Yeah.
cryogenic electronics because they
Right.
want to put some of that stuff at cold temperatures. But
Closer. Yeah.
but unfortunately, the you've got to get from those chips that are sitting at a few Kelvin to millikelvin, and
Right.
that is a real challenge. You then
Right.
have to have all the wires, and you have to be able to thermally isolate. And so when you see these pictures of the superconducting qubit fridges, it looks like a chandelier.
Yeah.
All of those cables are to take signals from the millikelvin up to a higher temperature
Yeah.
stage.
Yeah.
You don't escape from that
Right.
if in that case. But
So.
yeah.
Oh, go ahead.
But because our qubits can sit at a very similar temperature to the classical electronics, it all can just sit in one module. So
That's fantastic.
yeah. So I mean, think about if you got your mobile phone, you break it open, when after it's gone out of use, and you have a look at the board on there. It's got so many chips integrated into a module with many
Absolutely.
high-speed links. Basically, we're looking at our quantum processor will look very similar to that. It'll be one module with many chips, some quantum, many of them classical, all sitting inside just one refrigeration unit.
Incredible. So, okay, there's one. You mentioned that you can't lay out the qubits in 1,000 by 1,000 grid.
Mm-hmm.
There are these smaller cells
Yep.
within the architecture because of the challenges of addressing all of those
Mm-hmm.
electrons in such a dense.
Mm-hmm.
So, is that still the connectivity of the small groups of electrons or single the qubits
Mm-hmm.
to the control electronics, is that still sort of a critical challenge ahead of you, or is that sort of a solved problem?
It's solved in terms of design. So we have all of the designs, and what we're doing at the moment now with our fabrication partners is doing a series of demonstrator prototypes, gradually increasing the integration and the connectivity.
Okay.
So there has already been some work done at the R&D level of doing this type of integration at cryogenic temperatures. We're working with IMEC and others in doing our first demonstrations of this just in the next year and a half.
Wow, that's
Yep.
fantastic. So that brings me to my last topic, which
Yep.
is, of course,
Time scale.
yeah.
When can you buy it, and what color
When
will
can
it
I,
be?
yeah,
Yeah.
or when can I play with it at least?
Yeah. Yeah. So look, Diraq has taken an approach, actually, which has got some similarities with, say, companies like PsiQuantum. One thing that we agree with with PsiQuantum is that in order to be truly commercially useful, you need to have a system at serious scale, and
Hmm.
so we set that scale at least of order 100,000 qubits, and preferably in the millions. So we've decided not to release systems at, let's say, the 100 qubit level, the couple of 100 qubit level. Um, we will make those available, let's say, to specific close partners
Right,
who want to
right.
gain some experience on them. We might do some bespoke project work for them, or for governments, etc. But as a first product release, we're targeting a system with many thousands of qubits. We're not publicly stating the number yet. We may well, maybe, I don't know, in a year or so, we might say what that number is. We don't want to give too much away
Right.
to our competitors. But our aim is that it will have sufficient number of thousands of qubits to have enough logical qubits to do uh, useful problems that are beyond the scale of existing classical supercompute.
Right.
And we're targeting that in the first half of 2029. So that will be a first product, and that will be a fully integrated product in a single refrigeration unit,
Hmm.
and with the error correction controllers. I should mention actually that the error correction controllers, and this is true for any quantum computing system, are going to have to be very high throughput, high speed
Yeah.
units. And those won't operate at cryogenic temperature. Those will sit
Right.
in a rack next to the refrigeration unit. But we believe we can get everything into a single rack, so keep the
Yeah.
overall thing quite compact.
And that external error correction computation, will that be CPUs, GPUs, ASICs, FPGAs?
That's
What's the horsepower like?
a very good question. I can't reveal
Okay.
our current strategy for that, because you
Fair.
appreciate that it's a little bit dependent on which particular partners we work with on it.
Of
But
course.
what I am happy to say is that we believe that there are a variety of different pathways that can go. Using standard GPUs, we think is possible. Custom ASICs, definitely also possible. The exact blend really is a matter of, let's call it supply chain development time and cost.
Of course. Yeah.
But all of the above are possible, and we're currently speaking with partners on each of those solutions.
Well, Andrew, this is super interesting. It's really fascinating to me how, you listening to, you're clearly thinking about industrialization and commercialization. And that's such a clear contrast to sort of the earliest days of qubits, when it was clearly just a science experiment. But we've been sort of gradually moving through this, foundational science, basic science, and then sort of getting more and more capability. And listening to you, it's really clear that your bet is on the threshold of sort of industrial value, commercial value, and industrial scale being in the very near future, which I think is super exciting.
Well, Sebastian, I just want to, really, just as a final point, emphasize that, because our view is that you're not just going to have one or two of these gigantic energy-hungry quantum computers. That is not a commercially viable pathway for this technology. If we want quantum computing to be ubiquitous and used widely, there are going to need to be thousands of quantum computers, separate quantum processors that are integrated with high-performance computing, GPUs, and so on. I've actually in fact, I'm sitting at the moment at NVIDIA's GTC day. They've just had a quantum day, and a lot of the discussion has been about the integration of AI with quantum, using quantum computers to provide essentially the high quality data that goes into the models for example, for drug design and so on. But for that to work, we need to have a data center that's going to have thousands of quantum computers.
That's right.
And that's only going to be possible if we can make them affordable and compact. And that's been the mission of Diraq from day one.
Right. Well, fantastic. I look forward to hearing more as you progress. And thank you so much for joining us. It's been really, really interesting. Thank you, Andrew.
Really enjoyed the discussion, Sebastian. Thank you. Bye-bye.
Thank you for listening to another episode of the podcast, a production of the New Quantum Era, hosted by me, Sebastian Hassinger, with theme music by OCH. You can find past episodes on www.newquantumera.com or on Blue Sky at newquantumera.com. Thanks again to the support from APS for this episode. If you enjoy the podcast, please subscribe and tell your quantum curious friends to give it a listen.